I'm just giving the others a couple of minutes to join in. In the meantime, if there are any questions on the assignment, I'll be happy to take them. One or two people sent me messages for clarifications, and I have responded. But in case something is still not clear, please feel free to bring it up at any point in the class.
Maybe you can share the clarification if you don't mind, if
Oh,
they be relevant to everybody.
yes, Mr. Malik, this is Malak. This is, essentially about whether AI tools can be utilized, let us say, for grammar checking. I think somebody asked in the class also, and I responded. An elaboration of the same question on, can I use them to do a synopsis of papers that I'm reading before I write the response, or different applications, not coming directly into document preparation, but using AI tools for their research and for final, let's say, edits of copy edits of the document. And I responded to them that that would be okay as long as you don't use AI for generating the document. I am good with your using it for your research.
Okay, thank you.
Thanks. Okay, great. We already have a cohort of 38 students. Excellent. Within, in first 2 minutes of the class, really 40 students. I really appreciate this. Let's get started. We are, welcome back to a new week of the AIML Foundations course. Both days we have supervised machine learning methods that we will study. Today, 8/8/26, we do, decision trees. Now, decision trees has spilled over from the previous class. It was supposed to be completed on the 2nd, but that doesn't matter. I will, adjust. I just, I'm mentioning that because this schedule is a live schedule. So it's not exactly the same one that I published on the first day. As classes evolve, I make little changes. So today we are covering decision trees and neural networks. Tomorrow, along with the ensembles, we also will spend, let's say, 20-25 minutes talking about SVMs. We won't go into SVMs in much detail, but I just need you to know what the term means. For those of you that are not aware, we will touch upon what SVMs are, but primarily all of tomorrow will be on ensembles. Then we have one more week of classes, where in the first class on the 15th of August, we will look into, essentially how ML happens in practice. How do organizations structure their ML teams? What life cycles do they follow? What kind of tools? What kind of metrics for ML success, etc. And then on the 16th, which is the last, class session, before we conclude on the 22nd, we we will do a lab for supervised machine learning methods. 22nd or Saturday will be the putting it all together class, and Sunday there is no class. 23rd, the deadline for submission of applications, submission of assignments is Sunday, and that would be the midnight Indian Standard Time, 11:59 p.m. on Sunday will be the deadline for the assignment. That's how we have structured it. And all of this is already mentioned in previous classes. It's even put on the slides in previous decks. So nothing new that I'm saying in terms of the schedule, just reading out what we have here. So after today's class, we have 4 more sessions left for this course. Let's jump right into today's topics. We have 2 substantial topics today. And clearly, like we have done so far, uh, for a machine learning method, the best that we will be able to do is to give you a quick, high level synopsis of the method. We are not attempting to make you an expert in building building nearest neighbor models, or building regression models, or building decision tree models. That is not necessary for this class. But you do need to know what these methods are, where they are applicable, what the current applications are, etc. So it's an intuitive synopsis of that class of techniques. Each of these are class of methods. When we talked about regression, we said there is linear regression, there is logistic regression. Then we said if you add regularization into it, then there are methods like lasso regression, ridge regression. So regression is a family of methods. Similarly, before that, clustering was a family of methods, time series was a family of methods. Nearest neighbor, when we came to nearest neighbor in last class, we talked about lazy learning methods. We said there are case-based reasoning, instance-based reasoning, exemplar-based reasoning. We mentioned multiple methods, all of which fall under the same family of nearest neighbor methods. And we talked about how nearest neighbor works and what its capabilities are. Likewise, today we will try to do two techniques. One is decision trees, one is neural networks, and we will do them at a quick, intuitive synopsis level. Particularly on neural networks, the rest of this program is about neural networks. If you think about it in one way, it's about Gen AI. And today, the primary implementation of generative AI happens on neural network models. So we will be doing a substantial amount of neural networks after Foundations of AI ML class. The entire deep learning class is about deep learning models, which are neural networks, artificial neural networks. And then even when we go into generative AI models, we will be looking at, let's say, how do you make these neural networks smarter, more resource efficient, less carbon footprint, how do you reduce energy consumption, etc. So we will continue to talk about neural networks even in the, to a certain extent, even in the generative pre-trained models class. And then we will go into application-oriented classes like, AI project design, execution, and impact, and then responsible AI. So there is a journey in which neural networks will be our primary technique that we'll hang on to after this class. This particular course introduces you to the other methods. Some of these methods we will come back to when we are, for example, discussing in deep learning, when we are discussing, the latest um, alternatives to transformer models, like state space models. Then we will look at how there are combinations of neural and symbolic methods that come in the same model in some of the latest models, because symbolic models, like the ones we are studying in this course, are efficient. They are very fast to run, and the cost of running them, total cost of ownership, is much less for symbolic models. Whereas neural networks are much more powerful. They can handle patterns that are much more sophisticated than what these models handle. So a combination of these two is utilized in the latest, alternatives to transformer models, to bring down the overall cost of overall cost, and also running time of real world models. We'll look at some of that when in towards the end of the deep learning class and in the generative pre-trained models class. But here it is essentially learning two techniques today: artificial neural networks. So I am really not going to be worried about building practical models out of artificial neural networks in this class. In fact, we may not even cover it in the, if time does not permit, we will not cover it in the supervised ML lab class. I'll ask Professor Saroja, I'll request her to focus on the remaining supervised learning methods and the ensembles, because those are some things you will not get to a lab in the future classes. But ANNs, I will ask her to leave out if time does not permit, because anyway, you will be doing multiple labs on deep learning networks, etc. So that's the context of where we are. First, let us get started on decision trees. These two are very different techniques. Sometimes the way that we draw them may show you similarities. Like a decision tree is, on the right side of this of this slide, we are showing decision trees. If you imagine the same thing without nodes, but with neurons on them, one could visually confuse it with a neural network-like structure, a feed-forward neural network-like structure. Upfront, I'm mentioning it, so you will keep away this confusion. Decision trees is a very, very different technique. Neural networks is a very different technique. We'll bring out the specifics of both of them. Even if there is some visual similarity, please ignore the visual similarity. Let's focus on decision trees for the next hour or so. What decision trees are used for is essentially extracting rules from data. We already saw one technique, association rules, that extracted rules from data. Association rules used unsupervised data sets. They didn't need a ground truth. They only looked at, market baskets and found associations between market baskets, between items and market baskets. Decision trees look at supervised data. And so an example data set is being shown on the left side here. This is on, whether somebody is likely to cheat on a tax return. Okay, we are looking at a potential fraud situation. So there are three columns, which are the attributes. There are a few examples. We have 10 examples here. And there is a class here. The class is whether there is a chance of this customer cheating on their tax returns or not. And the attributes can be of any type. The features can be categorical or continuous. We're taking a very simple toy data set here. So if just to read out the first row here, I hope you are able to see the font size. This is a person for whom there was a refund. This person is single in their marital status. They have a taxable income of 125,000, let's say, dollars or pounds. And they did not cheat on their tax filing. So this is all historic data. So it's right for me to use the past tense. Why do I say that this is historic data? Because there is ground truth available that they have cheated or not cheated on. Similarly, I'm taking one more random example. I'm taking row number 5. This person did not get a refund, and they are divorced in their marital status. Their income is a little less than before, 95,000, let's say, dollars, and they did cheat on the thing. Like this, you may have thousands of examples of past data, cheating, non-cheating. Maybe here, if you see out of the 10 examples, 3 of them are cheating. So about 30% are yes examples and 70% are no examples. For some other problem, it could be equal distribution. For some other problem, it could be only 10 examples out of 1,000 that are in the yes class and other 990 in the no class. So this could be anything. Similarly, you could have millions of examples, millions of rows in the data. You could have thousands or hundreds of thousands, even up to hundreds of thousands of columns in the data. You may have any number of classes in the that you're trying to model here. Here, this is a binary class problem, only yes and no. But if I was, for example, looking at what amount they cheated for, yeah, and I pin those amounts, there could be a dozen classes here. People who cheated for an amount of $0 to $1,000, $1,000 to $10,000, so on and so forth. There could be multiple classes. So this is either a binary class problem or a multiple class problem, and it can have any number of attributes of any types, and it can have any number of training examples or instances. And each of them is a historical data point with a ground truth data, with a ground truth label. That's what we get in the data that is supplied to us in this supervised machine learning method of decision trees. In fact, this is the type of data table you will have for any supervised machine learning method. Whether it is a multivariate regression, in which case you won't have the categorical variables. You will have everything as continuous, so the type might change. In linear regression, multiple variables. If it is a logistic regression, multiple variables, all will be categorical. All these examples will be categorical, all these features, I'm sorry. If one of the features is continuous, it is possible that we can, have we can bin it and convert it into a discrete and then use logistic regression. If it's a neural net, if it's a nearest neighbor method, you can have either categorical or continuous, and you can have any number of classes in the nearest neighbor also. So this table, the reason I took time to just talk about it a little bit is because for any supervised learning methods, this is the world. This is all they know about the world, the supervised ML method. It does not have any other insights into or context about the attributes, the way the data is prepared, the new data points that come dynamically. No supervised machine learning method has access to anything other than this table of data. This table is the entire world that they have. Right? It's important to understand that, because these symbolic machine learning methods, even artificial neural networks, your data eventually looks like this. It could be an image you're feeding. It could be a bunch of cat and dog images you're feeding, and your network is classifying cat and dog. But internally, the image is comprised of pixels. So you can imagine that these are just pixels with a label, cat and dog, that are being passed on. So this is the overall worldview of a supervised learning classifier, and decision tree is no exception. The output of, things happen in two stages. We have talked about a stage where a model is being learned and a stage where model is being used. So this is learning or model building. This is inference. At the time of model building, what we do for a decision tree is look at this data and build, first find the best attribute to split the data on. You can see that the data, the classifier is working by splitting the data along instances. So, some of these 10 instances go to the left side, some of these 10 instances go to the right side. Let's say, as an example, if when we say refund, is refund, we know that refund is a categorical variable. It is taking only two values. And there are three, people for whom the refund was yes, 7 people for whom the refund was no. So in this yes stage, to the yes side, refund was yes. The 7 of them go away to the, 3 of them go away to the left side here. Okay, 3 where refund is yes, go to this side. So the data is being split into 3 examples on the left side and 7 examples on the right side. These 3 examples, if you look at all the yeses here, all of them are no for cheating. You can look at the table. Wherever there is a yes and a refund, cheat is no. You can double check that. So we do not need to split this anymore. All of them are no for the class label. So we just create what is called a leaf. These yellow nodes are called the test nodes or splitting attributes. Okay, both of them are alternate ways of saying the same thing. They're called the test nodes. They're called test nodes or splitting attributes. So refund is used as the splitting attribute, and left side, the blue ones are the leaves. We are creating leaf nodes. So this leaf node, its label is no because all its examples are no. And its size, if you look at, is 3 examples out of 10 examples. Although we have not marked it, it is 3 examples. The other 7 go towards this side. And then these, we are splitting on an attribute called marital status. How did I know to split it on refund here and on marital status here, etc.? That we will come to. How to that's the crux of the matter. How do you build the tree? But imagine that you have a black box model that does some computation on the data and spits out what attribute to use. For now, you imagine that. We will show what that model is, what that mathematics is, to identify what variable to use as the splitting attribute. So here
even
I'm
in this example,
splitting
Doctor,
on.
if you
I'm
allow
sorry.
me,
Yeah, Mr. Hirzala.
in the case where no for the refund, the marital status varies. Some of them are single, some are married.
Yes.
So that split doesn't have any impact on the result.
So this is why we are splitting on marital status, Mr. Hirzala. The refund, when we do a test, refund equals no, then 7 examples come here, some of which have, all of which have refund, of course, as no. But they have, some of them are single, some of them are married, divorced, and taxable income is varying. The labels are varying across the 7 that where refund is no. So it is necessary to split them again. See, our goal is to form these homogeneous leaves. Okay, we are trying to divide the data using hierarchical partitioning of the data and want to bring it to a level where they are, each group is homogeneous in its label. When we say a group is homogeneous, we mean the class label is the same for all examples. So we split on marital status because we want to get to homogeneous partitions. At this point, when 7 examples come down after the refund equals no test, in these 7 examples are heterogeneous. It's a subset that is heterogeneous. So we split it on marital status, hoping that we can go towards homogeneous, class labels in each partition. Does that make sense, Mr. Hirzala?
In a way, yes, but still,
Okay.
I'm failing to understand.
I will
Because the
elaborate
blue,
how that variable is chosen in the next slide. Maybe that will clarify. Sorry, I didn't mean to interrupt you.
sure.
And Professor, is it always split into two?
Mr. Bharadwaj, can we let Mr. Hirzala finish, please?
Oh, okay, sorry.
I'll wait for the next slide where you explain how we came up with it, and probably that will explain.
Okay. And Mr.
Thank
Upadhyay, your hand is up, and then I'll go to Mr. Bharadwaj.
Yeah, so if I understand correctly, so in nature we have a tree, right? So it starts from the trunk, then probably two branches, then towards the leaf, we start going towards multiple branches and much smaller branches, right? So I believe
Yes.
this is the same kind of concept where you start with something or an attribute which has have a one or two values. Then if there are attribute which has have a more values, right? So that's way your distribution would be much more, I guess, even starting from the first node, I guess.
Um, uh, The example with the nature is correct as far as the structure is concerned. It's just that this tree is upside down, its root is on top, its leaves are on the bottom.
Correct.
So except for that, the comparison on the structure is fine. The comparison on the sizes of the branches is also not inaccurate, in the sense that at the root, near the root will be the largest amount of data. And as
Correct.
you
Yeah.
keep splitting, the partitions become smaller and smaller all the way down. Where it is not correct, I mean the comparison where it is not applicable is on how the variable is chosen. We are not choosing the variable such that there is a there is a leaner split or a bigger split, etc. We are choosing it. I'll show that in the ensuing slides. We are choosing it such that the partition becomes homogeneous. Even if it's a very
Okay.
small partition, we're interested in homogeneous partitions. Okay, so
Okay.
we'll go there. Mr. Bharadwaj?
Perfect.
So Professor, my query was, so probably can we split it into more attributes, or is it only two? Because say probably this categorical data of marital status, there are three classes. So had we divided it into three, our stages to reach the decision would be shorter, right?
Yes, it could be the case. So in practical decision tree software, you will be able to do non-binary splits. However, this particular algorithm which is being used here, which is called C4, it uses binary splits. So each split is required to be binary, but there are algorithms that will allow you to do a non-binary split here. More often than not, we the default methods of decision tree that we utilize, a majority of them are using binary splits. So because I'm just introducing decision trees, I have used a binary split here. But you are right. It is possible to do a multi-level split. And it's possible that in such a case, I don't know for this data, I have not computed it, but it's possible that you will reach leaves faster, which means that your height of the tree can be reduced if you use non-binary splits instead of binary splits. So that observation is not inaccurate. This is just a artifact of the algorithm we are using here to split, and that algorithm will look into in the ensuing slides. Okay. Mr. Krishnamurthy.
Hi, Professor. Thank
Hi.
you. What I would like to understand here is like, now we are actually, based on this example that was cited, we are actually looking into the value of the taxable income. Like we want to know because it's less than 80K or more than 80K, right? But
Yes.
if we want to build this decision tree based on the cheat or no cheat, obviously the splitting attributes will differ, correct?
Yeah. So yes, Mr. Krishnamurthy, but we will not split it on the class label. See, this is shown in red because this is a class label. Class label is our ground truth, and a decision tree splits only on the independent variables. It doesn't split on the dependent variable. It splits on the independent variables with the hope of partitioning the data into subsets where every subset is homogeneous in terms of the dependent variable. So we never split on the independent.
No, what I was not meant to split based on the class, but the objective, if let's say we want to look at the cheat or no cheat, that is what we want to look at, right? Then obviously your class also changes to some other variable, right? It shifts the position. Like for example,
if your
refund
data
will become the class, and then the thing when shift, right?
If your data were different, that cheat become, if cheat were
categorical, for example, and
independent variable, it's always a categorical, but it is, if this were an independent variable, let us say if taxable income was the dependent variable, then you would build a different structure. Yes.
Right. Okay. That's what I want to know. Yeah.
Great.
Thanks.
So we said stage 1 is the model building, stage 2 is the inference. So during model building, we split 10 examples using the feature refund, and 3 went this side, 7 came here. These 7, imagine that there's a black box which does some calculation on the data you have and spits out the variable that you should use to split, the independent variable that you should use to split. Let's say that spits out marital status. It will also tell you that single and divorced should be on one side and married should be on the other. So here we are only trying to understand this structure. So single and divorced, if you take in marital status where the refund is no, then you have, let's see, 1 here, 2, 3, 4. So 4 of them would come towards left side, single and divorced, and 3 of them would go to the right side. And none of the married people among the no's have cheated. So they're all no. So you get another homogeneous leaf here of no. So 3 more examples here, 3 examples here. The other 4 have come here. And these 4 are being now split on the basis of taxable income. If taxable income is less than $80,000, they have not cheated. If it is greater than $80,000, they have cheated. So that's the structure which is called decision tree, which is completely built out of this table of data. Please understand, I hope you understand that this structure has really no knowledge other than what is available in the data. It has no other insight into the problem of catching cheats than what is already given in this table. And in this table, we are making simple splits. Is refund yes or no? So it's a binary partition we are doing. Is marital status single, divorced, or married? Another binary partition we are doing. And taxable income. The entire data examples here is divided into 4 regions, all of which are homogeneous in terms of the cheat label. Each one of them is homogeneous. There is no impurity. Impurity is the word we use. There is no impurity within each leaf. Impurity means that it may be dominantly yes, but there may be one noisy example there, one no there. Then we would say that there is an impurity. So if you imagine the data set here, we said 3 examples went here and 7 examples were here. These 7 examples had impurity. Not all of them was one class. But we build the tree all the way down so that every leaf is 100% pure. There is no impurity in terms of the class label. The other observation is the tree is nothing but a collection of if-then rules. If, for example, if I want to describe these guys, then if they have not received the refund, and if their marital status is single or divorced, and if their taxable income is less than $80,000, then they have not cheated. So it's an if of 3 conditions. It's a conjunction of 3 conditions, and. If refund is no, and marital status, so on. So conjunction of 3 conditions on the left side. So the antecedent of the rule has 3 terms, 3 conditions, and it's a conjunction. And the class label is on the right side. It's a consequent. Class label, just like in association rules, anything can be on the left side, anything can be on the right side. We have not restricted that all, on the right side, there should be a single variable. Anytime, if bread, then butter, if butter, then orange, if, you can have any kind of rules in association rules. Whereas in decision trees, you're restricted that in the all the if-then rules that this tree is succinctly representing, there are how many if-then rules are there? Each leaf is one if-then rule. So since there are four leaves, this tree is essentially four if-then rules. Out of the four, three of them have no on the right side. One of them has yes on the right side. So if I were to describe this no, as a single rule, then it will be a disjunction of conjunctions. If you know this terminology, if you don't, just ignore what I'm saying. I said each rule is a conjunction if refund is no and marital status is divorced or single, and divorced single, or and if taxable income is less than 80,000, then it is no. This is a conjunctive rule. If I have to describe all the no's as a single rule, then it will be if refund equals yes, parenthesize, or if refund equals no and marital status and tax, or. So there will be three ors. So it's a disjunction of conjunctions. That will be, if I am to give you a single rule for the class label no, then I have to give you a disjunction of conjunctions. Every path from the root to a leaf is a single rule. You cannot do a rule midway. It has to come all the way to a leaf, because the right side of the rule, the class label, exists only at the leaf. Okay? That's the structure that we are inducing from the data. Once such a structure is induced, you use it for inference. So when a new example comes in this case, we have a new example, which is a test data. A new person who didn't get a refund, who's married and has a taxable income of 80,000. We don't know whether they can be a cheat or not. So it came in live. Let's say this instance, this data point came in live, and we want to classify it. All we do is take this example and drop it through the tree. That's the terminology we use. We drop it through the tree. So we first check whether refund, what's the status, what's the value of the feature refund. Refund is no. So we go to the right side. Now it's married. So we go to the right side. Hence, the label is cheating will be no for this new instance. Once the tree is built, any number of test data items it can classify simply by dropping the example through the tree. Okay. If this example has any missing data, let's say if we don't know the marital status of this individual, then you need some kind of cleansing upfront, or some kind of imputation of missing values upfront before you can use the decision tree to classify this. So if test data has missing values, you cannot directly classify it using a decision tree. You will need to first impute the missing values, especially if that attribute is being used in the tree, you will have to first impute it. So building and using. Building is if-then rules are captured as a tree. And the way this happens is we divide the feature space into distinct regions. I hope you're able to see that all these regions are non-overlapping. This is, so the same example cannot go to two sites. Examples have to go to a unique leaf. Okay, in this particular variant of a decision tree algorithm, examples can go to a unique leaf. So all leaves are distinct and non-overlapping. And at the time of using, every observation is dropped through the tree and lands at a leaf node. And the label that it gets is the most common label at that leaf. So even if this leaf were to have some impurity, we still can assign a label because there is a majority label. That's how the classification would work. Yes, Ms. Raghuraman.
Professor, can we say that when there is, I'm just looking at where this could possibly have applications. And if we are looking at a data set, can we say that, if the data set is having mixed data, like both categorical and continuous, and if the outcome that we are looking for, or the independent variable that we are looking for, has is a class data in terms of binary or whatever it could be,
The
provided
dependent
these,
variable.
the dependent, sorry, in which case, a decision tree is used, or is it that, that's not the right way to look at it, and it could be used for, certain other ML algorithm
So
or models could be.
if I paraphrase your question, again, just to make
Yes,
sure that
please.
I'm answering the same thing,
Mhm.
you're asking if there is a data set where the class label is discrete, but the independent variables can be either discrete or continuous, then decision trees is a technique that you can use. This is
A
your question.
technique or the technique? That was my question. Also,
Sorry?
my other question was: is it the technique or a technique? Is it that
It's
this
a
is
technique. It's a
okay?
technique because you could have used nearest neighbor for this data set. Nearest neighbor also, can take it can compute. There are formulae for computing distances between categorical variables also. So nearest neighbor can work with attributes of any type, any number of classes, etc. You can use this with neural networks. So decision tree is one of the techniques. And also on the other side, even if your class variable is a continuous value, then in that case, the tree would be called a regression tree instead of a classification tree. But decision trees are good for both discrete classes and continuous classes also. I'm showing the example I'm showing here uses a discrete class, but regression trees are also common.
So
Okay,
then
so
what
it's
we look for is the independent variables, whether they are a mixed lot in terms of being categorical and continuous.
no, ma'am. I'm
Oh,
saying that whether your independent variables are categorical or continuous or a mix of those, whether your class label is categorical or continuous or a mix, for any supervised data set, there exists decision tree algorithm that you can utilize. And decision tree is one of the methods only. So to answer your question of, so when do we use decision trees? When is a preferred time to use decision trees? I think that's where you're driving at.
Yes, please. Yes, please.
We use decision trees because they are intuitive and they give us if-then rules. They don't, for example, in nearest neighbor, all we get is a bunch of local neighbors on the basis of which we are determining the label of a new point. Whereas in decision and in a linear regression equation, it's an equation that you get as an output. So your model is a mathematical equation in regression. Your model is a bunch of points in lazy learning methods. Your model is a set of if-then rules in decision trees. And if-then rules are easy for humans to understand and trust. So decision trees are used in cases where explainability is very important and you get if-then rules. And also decision trees are very rapid as classifiers because when we get a new sample, see, even if you have to drop it down 20 levels, it's
There's no
almost
calculation per
instantaneous.
se. Yeah, I
Yes.
can see that it will be much faster.
Yeah.
I just
So
goes on
speed
splitting it.
and explainability. That's why we use decision trees, not because of the attribute type or class.
Application. Oh, okay, okay. But I'm still not able to see how we can use linear regression for this data set.
For the regression, I didn't say, ma'am. I said we can use nearest neighbor. For regression, you must have all continuous values. Linear regression. For logistic regression, you must have all discrete values. So you cannot use regression.
Yeah, so regression is not possible. KNN and neural, yes.
Yes. KNN, the decision trees, neural networks are possible.
Great.
Mr.
Thanks a
Kandan?
lot.
Sure.
Professor, just a follow-up question on the same thing. If we don't use the right model, then the end result will not be correct, right? So for example, where we are using decision tree, if I use lazy learning, the result will be two different results, right? It cannot be the same result. It cannot be what we are looking at. So we'll have to choose the right method or model for us to achieve the end results. Is my understanding correct?
That used to be the case. People like me, when we were learning machine learning, the primary skill set you acquired was looking at a data set, being able to, take a educated guess on which is the best method to use on that data set. But it is irrelevant now because each of these is one tool. So you can run all the methods that are applicable for this type of data set. You can run all the methods and choose the method that gives you the most accurate classifier. A classifier that has, let's say, best classification accuracy on unseen data, on a validation data set or on a test data set. You can pick that. So it's not that you will go wrong terribly if you use a method which is not giving you the best answer. Today in machine learning life cycles, you essentially run your tool with multiple methods, and in fact you can set it up such that it recognizes what are the methods that are suitable for this data set, runs all of them with different parameter combinations, and comes back to you saying this particular method with this parameter combination works best for your data. So that way you won't go wrong by looking some other method. Yeah. Okay. Yes, Ms. Raguraman.
Sorry, but then, Professor, if we are learning each of these methods and their applications, and then we have an assignment that's coming up where we need to look at our own data and figure out which is the best ML method that is applicable or appropriate, then we should be able to look at the data and be able to figure out what is to be used, right? Yes, we can completely depend on the system to figure it out for us, but wouldn't it be good for us to know based on how the data looks?
So,
at least in this later learning stage.
Sorry, go ahead, please.
Sorry, I said, wouldn't it be better for us to know, at least in this learning stage where, we need to kind of understand each of these.
Two parts to that answer, Mr. Raghuraman. One is that the assignment carefully does not ask you to find the optimal ML method. It says, please choose one use case, please choose any method that can be utilized there, and talk about the application, talk about the evaluation metrics you will use, data, feature engineering that you will use, etc. So you're essentially walking through one real life machine learning application, like experiment. It's not the assignment is not giving credit to you're using the best possible method on that data. This is one part of the answer.
Okay.
The second part of the answer is that this is exactly what we are trying to do in each method, give you an intuition of where a particular method should be used. So if it is a market basket analysis, you would go ahead and use association rules. But if the number of items in your inventory are very large, then you cannot use association rules. You would instead jump to collaborative filtering. If you have a data set where you don't want to do any computation up front, and because your data may be drifting, you don't want to build a model, then you will use nearest neighbor. So for each of the methods, we are trying to provide an intuition of what is even in this case, I was saying, when you need explainability, because if then rules are explainable, when you need speed, when you need a simple classifier, then decision trees are a great technique. So we are trying to provide that intuition for every method. But the assignment itself is not looking at you to have the skill of picking the best possible method for a data set.
Okay, as long as we are not totally off, I mean, we would still need some level of intuition, I presume, because we cannot take something which is like totally off.
Yes.
And we probably realize that when we try and apply it to whatever data we have. There quickly, probably an intuitive approach would be far better.
I agree with you. So the that level of intuition that one has is, okay, is this going to be a unsupervised ML problem or a supervised ML problem? If it is a supervised ML problem, is explainability important to me, or will a black box be okay? And if in that, am I likely to, will a simple linear classifier be sufficient, or will I need a sophisticated nonlinear classifier? Is the problem complex enough to need a sophisticated nonlinear classifier? In which case, we have not yet talked about them, but you may jump to an SVM or a neural network, etc. So that kind of intuitive thinking about the problem is absolutely necessary. You're right. But what I am not looking for is for you to be able to identify the optimal method for that, because
I get
I
that.
think that's
Yes,
not
yes.
needed.
Yeah. And also because we are not working with the data, we'll never know whether it's optimal or not.
Exactly.
Because we're not figuring out any errors or anything. But
Yes.
just to take it off from there, I had this question in my mind is, wouldn't it be good to have the assignment submission a few days after putting it all together a session? Because the way you just explained, right, if I look at the data like this, then is this good or is this good? And then if this is the one, then it's, at least in my case, I'm not even familiar with all the methods. So to look at it that way, I think I feel everything is applicable to anything, or vice versa. I'm sorry, I seem to sound very ignorant, but
No, not at all.
that's how muddled I am today.
You're raising valid points. So I want to reassure you that this class where we are discussing ML in practice, which is the Saturday of next week, there we are going to be taking, going through the life cycle of an ML problem. So the first, how do you look at in the exploratory analysis stage, what is it that you will identify? Then how do you do feature engineering, so on and so forth. So when you go through the life cycle, I think that's what is needed, and you will have 7-8 days after that to. So putting it all together is more of like say helping you transition from this course to the next course. That's a bridge. Putting it all together is a bridge class. But your ML summarization will happen in next Saturday itself, which is the, before the lab session.
Fair enough. Thank you so much. Thank you.
Mr. Khedkar?
Yes, sir. Just adding to this particular discussion, the way I understood the assignment, I'm just trying to reaffirm that particular part. When we talk about this particular assignment, it is more of a writing up my hypothesis. The problem I have, how do I identify that problem? What is the exact solution which I'm looking at? And what would be the best solution based on my basic understanding, high level understanding of these machine learning algorithms, which suits it most, and why it suits me, this particular part. That's the assignment, right? Means that's how do we put that hypothesis together. Then you go for the proof of concept kind of stuff. Before you go to the POC part, this assignment helps you in putting the problem together, building your hypothesis based on the learning of high level understanding of these particular models, and that's all, right?
Minor, I mean, most of what you said is, I agree with. A minor change is, you said choose the best possible method. I'm not looking for the best possible method. I'm looking for any suitable method for that problem. And then you're explaining, why you chose that method, or what, how you work with that method. So it is a thought exercise. You're right. Understanding area, like knowing what a real world problem is to which you can apply a machine learning algorithm, picking a possible machine learning method to be applied there, and then walking through what stages this has to go through to build a machine learning model on that problem using this algorithm, that your method that you have chosen. That journey, that thought exercise is what you're capturing in those 2 pages. So most of what you said is fine. I just want to clarify that I'm not looking for the best possible method. Okay. Any suitable method is fine.
Yeah. But when I'm putting it together, based on my logical understanding of this particular part, what suits me means what, based on the problem and everything, based on my analysis, I would like to identify one suitable method and I would have why I'm choosing that particular method.
Yes.
That's it, right?
Yes.
Okay,
Yes.
that's
You will say that so you may add a couple of sentences like I just said that explainability is important to me. So I'm not using a let's say a neural network. I'm using a decision tree. That kind of why you are using that, why you are choosing that one possible method, you will express it somewhere. Yes. Yeah.
Thank
Okay.
you.
Great. So let's move on to the next thing. The next insight is that this tree that you are seeing, the decision tree we build, is if the attributes were continuous, because I want to I want to display them. So visually, I want you to relate to it. Imagine a problem where the attributes, there are only two attributes, two independent variables, not three like we have here. And imagine that both of them are continuous attributes. And there is a class label, which is a discrete value. So we have already seen the geometric intuition. Any table of data like this corresponds to a geometric space where, let us say, no points are blue points, and yes, cheat equals no is blue points, cheat equals yes are red points, and it's a space where this data is distributed. Because I want to show it on paper, I'm saying there are only two independent variables. So it's 2 dimensions. I can show it on paper, or show it on the slide. So let's say this particular, on the right side here, I have a problem where there are two types, it's a 2-dimensional two independent variables, age and income. And the classification is that there are some people that have attended a concert called Burning Man and some people who did not attend. So the blue triangles are people who have not attended, and we have plotted their age and income. The orange circles are the ones that have attended the concert. We have plotted according to their age and income. Now, when you do a decision tree on this, what's the equivalent of a decision tree in geometric terms? That's what I'm trying to show here. The equivalent is splits like these. The first root split essentially splits the entire data set into 2 partitions. So the root here is income is less than or equal to 60,000. Yes, guys will go below this 60 line. Why no people will be above. So this line, what I'm trying to say is this line is equivalent of one test, which is income less than 60,000? That's what we are showing in this slide. Now, on the left side of this, it's not fully pure because you see some impure points here, but mostly it is a blue triangle area. So like we had in the earlier decision tree, we saw the root node on the left side of the root node, on the yes side of the root node. The root node is income less than 60,000. On the yes left side of it, on the yes side, you have one label which is did not attend. And it so happens that this this leaf node of did not attend is not completely pure. It's not 100% pure, but it is negligible. The impurity is negligible. Hence, we keep on the left side, we keep it as the did not attend class. I am just seeing there seem to be some how to choose what. Yes, Mr. Islam, I will talk about how to choose the feature. I have not yet come there. Mr. Chan, what advantages or disadvantages of binary decision tree compared to multi-way splits? Binary trees are simpler to simpler to represent visually. Simpler in terms of their representation. Even as trees, they are simpler. But sometimes by using non-binary splits, if your attribute is non-binary, you will be able to reduce the height of the tree. So you will have fewer antecedents in the if-then rule to get to a leaf. Shorter tree means that your leaves are in terms of number of tests are closer to the root node. So if there are only 2 tests along a path from a root to a leaf, then you have 2 antecedents in the left side of that rule. So the advantage of a non-binary decision tree is that it might be shorter. The disadvantage, I mean, there's no such a great disadvantage. It's just that algorithms were, original algorithms like information gain, like C4, were written for binary attribute splits. Later, I mean, an algorithm like classification and regression trees, CART, which is another decision tree algorithm. CART was written to handle multi-level splits. So it's just a limitation of the algorithm. Really no disadvantage of doing that. Okay, I am just reading. Mr. Kedkar, for the data pipeline is not expected. Okay, great. So we said on the left side, there is just one leaf. On the right side here, we have, let's say, imagine that this is the next split, the second level split. We are splitting it at age less than 29 years, let us say. I mean, this is 30. So I'm taking that this is 29. Age less than 29. You can do less than or equal to, or you can do less than. If you do less than, all the equal tos will fall on the right side. So if you do age less than 29, then all these guys will be in one leaf. This is again another impure leaf with a did not attend label. On the right side, you'll have to do one more split, which is this, which could be age equals about 30, age less than about 39. So the point is that this geometric representation corresponds to a decision tree which has a root node, one leaf on the left side, one test on the right side. This test, on the left side of this test, there is a leaf node. On the right side, there is another test. For this test, there are leaves on both sides. So it is a 1, 2, 3, 4 leaf decision tree with 3 nodes, 3 test nodes. So that I think what I'm trying to say is, between the visual representation we saw of the tree, where we were hierarchically dividing, which what we saw on the previous slide, and the geometric representation, there is a one-on-one correspondence. A tree can be represented either like that tree diagram you have seen, or it can also be geometrically shown like this. Geometric, the limitation is number of dimensions, etc. So this, you do geometric representation only to get an intuition that what you are trying to do is divide the whole region into homogeneous partitions, more or less homogeneous partitions. This leaf you can see has a lot of error, many blue triangles in between. Although it captures all the guys who attended the Burning Man, there are many data points that fit in the same rectangle but do not have not attended. So it's a noisy leaf, whereas this is a less noisy leaf. This is an even less noisy leaf. So you can see visually, you can see that the purpose of a decision tree is to divide the space into rectangular partitions or hyperrectangular partitions if it is more than 2 dimensions. Hyperrectangular partitions, each of which is homogeneous in terms of class label. We tolerate some amount of error in each hyperrectangle, but it should not be too high. If it is too high, then we cannot be confident in assigning a class label. The purer a node is, the more confident we can be in assigning that label. And you can also see from this picture, you can also see that every partition is a linear surface. Every node corresponds to a linear geometric shape. So because you are saying income less than 60,000, it's a one line. Not only is it a linear, linear equation, but it is also axis parallel. It is parallel to the x-axis in this case. These two are parallel to the y-axis. Every split is parallel to some axis in these decision trees. Hence, they're called axis parallel decision trees. Axis parallel decision trees. So every split is an axis parallel line or a plane or a hyperplane. Line is 2 dimensions, plane is 3 dimensions, hyperplane is anything greater than 3 dimensions. So every split is axis parallel. Every region is a hyper rectangle. And regions, our goal is to divide the given data into regions, each of which is as homogeneous as it can be in terms of the class label. That's what a decision tree tries to do. The original surface that we, for the same data set, the actual best, separation may look like this. I'm drawing a nonlinear surface now for a data which is similar. It's not identical, but for a data set, the actual, surface, actual decision surface, dividing the, let's say, blue points from the green points from the brown points here, the decision surface might be nonlinear. What we are trying to do when we induce a decision tree, we are trying to approximate the nonlinear decision surface with a linear partitioning. So decision tree is an approximation. Decision tree is not capable of finding the nonlinear splits themselves. Here also, if I were to ask you, let me just try a very, very quick thing. I will, this will be necessarily ugly, so please excuse me. But what I'm trying to do is draw a line that just takes out, data points that are yellow. Okay. I am trying to do, let's say, like that. I hope you get the idea of what I'm doing here. I am simply trying to, capture all the orange points into one homogeneous region. And I'm not putting any restrictions on the shape of the surface that I'm drawing. I assume that I can find arbitrarily complex nonlinear surfaces. I have a capability of doing so. Let's say, there is still some error, but I got an amoeba shaped thing, which is capturing most of my orange points there. This may be the original surface. What I drew may be the original decision surface in nature, which separates those that attended and those that did not attend. From all the past concerts, I can take all the past concert data, age and income of everybody who attended, and draw a original, decision surface which separates those that attended from non-attended. Now that is the decision surface that I'm trying to approximate. Decision trees approximate it with splits, axis parallel splits, and rectangular regions. This one has only 3 splits, 3 tests. But you can imagine that I can continue splitting further and further until I get to regions which are very, very small but completely homogeneous. If age and income are not sufficient to separate points, then I might include more attributes and tessellate the data. Keep partitioning it hierarchically until I get to rectangles, which can be arbitrarily small but completely homogeneous. Each rectangle has only one label. So what I'm trying to say is a decision tree is a linear hierarchical approximation of a non-linear surface, which is the decision surface we are trying to reach. Decision tree by itself cannot give you, this particular algorithm cannot give you non-linear surfaces. Hence, it approximates it by using many splits. You can build a very deep decision tree, 20 levels deep, 40 levels deep, 500 levels deep decision tree, and approximate that surface by tessellating the space into hyper rectangles, each of which is homogeneous. That's what we are trying to do when we induce a decision tree. Let me pause there. Is this making sense to you? If you have any questions, I'll be happy to clarify. Yes, Ms. Raghuram.
If I were to not use a decision tree and arrive at a nonlinear decision surface or boundary, as what would be the other method that can be used, please?
Neural network. Neural network gives you that arbitrarily complex nonlinear surface. That's why deep learning is winning. In many of this. And support vector machines can also give you a fairly reasonable, nonlinear surface. K-nearest neighbor can give you a very nice nonlinear surface. That's why we said, K-nearest neighbor will never have error that is more than twice the Bayes optimal error. The reason is because it is able to approximate, it's able to arrive at, go to arbitrarily complex nonlinear decision surfaces.
So then amongst the methods that we have learned so far, KNN is the one which we could use.
Yes.
And going forward, we might learn a couple more.
SVM and ANN.
Right. Thank you.
Yeah.
Thank you.
Okay.
Doctor,
yes.
Just one quick question. Like, for example, right? So decision tree, you mentioning that it is approximation based on homogeneous method, right? Something of that sense, right? So what happens if, let's say, if it's too homogeneous? Like, for example, now we can divide into these things, but we can also have multiple of these things, right? So or you can have,
you can.
multiple,
it need not be a single
goes
region.
into like 50, 60 branches like that, right? Then
Absolutely.
it becomes too complex as well, right?
Yes, it does. But these are not, today, if you have, I'm showing small data sets on the screen here. Let us say if you have a data set that has 1 million instances, let's say 40,000 dimensions or 4,000 dimensions or 400 dimensions even, then you necessarily will have multiple regions. Imagine that there is a 400 dimensional space, millions of points, blue and orange points that are distributed in that space. And you're trying to draw rectangles, each of which is homogeneous, then there'll be a large number of those rectangles and if your data is not textbook data where it is simply divisible into a few rectangles, in any real world problem, you will have a large number of rectangles, which just means that your decision tree will be large. But let's say that this 400 dimensional space with a few million examples, let's say you divide it up into 5,000 rectangles. Okay, I'm just taking a number. 5,000 regions. Here there are 4 regions. Like that, I'm saying there'll be 5,000 regions in some larger problem. However, 5,000 is the number of leaves of the tree. Some of you who have done geometry, computational geometry, know that a binary tree with 5,000 leaves has log of 5,000 as the height. So it's not a very large number in terms of height. Within, let us say, 12 splits or 13 splits, you will get to 5,000 leaves. So, if it's a more or less balanced tree. So my point is, even if there were 5,000 regions, every if-then rule is only 10 to 12 conditions long. So it's still practical. So that's the beauty with decision trees, that even for a very large data set in higher dimensions, building the decision tree is quick. And after building, inferencing is quick because your complexity of inferencing is log of the total number of regions, not the number of regions themselves. And because it's a tree, if it's a binary tree, if it's a balanced binary tree, we know that if n is the number of leaves, log n is the depth of the tree. So that's why you're able to do both the inferencing, particularly really lightning fast with decision trees, and it's explainable, and that's what is the attraction of that method.
Yeah. Thanks, Doctor. I have a follow-up question as well. In the previous example that you showed with the simple three categories and one class, right?
Yeah.
So in that example, I think when we look at the inference of it, it is actually accurate in a way, right? But why do we say that it is only approximations in your explanation earlier? Why do we call it as approximation when it's accurate? Yeah.
Yes, I was by no means saying that decision trees are not useful because they are approximate. I was actually trying to make two different points. Decision trees are, have been the most favorite method for a couple of decades. Decision trees, the popular algorithms of today were developed at the end of 70s. Until the time that, until 90s, of all the methods, of all the machine learning methods, decision trees were the most followed by the community because they were efficient, they were accurate, they were easy to explain, intuitive, so on. When ensembles came, ensembles are essentially groups of decision trees. Random forest, for example, a forest is a collection of trees. So we'll talk about ensembles tomorrow. But after decision trees, ensembles of trees became the most popular technique. So your random forest, your XGBoost, such methods. So in a sense, for about 30 years before deep learning took over as the most well explored method, the community of machine learning and worldwide community used decision trees as their default method. So it's actually a preferred method. So there is absolutely no connotation of my say when I said approximation that decision trees are not useful. The approximation part I was pointing out only to say that there are problems where the decision surface may be a very sophisticated nonlinear separation between the classes. For example, if I am trying to separate between students who are likely to take liberal arts when they grow up, let's say we are looking at students in their first grade or second grade and trying to see where they will shine in liberal arts or in legal profession or in STEM, etc. That space, if you're having millions of students, that decision surface is probably a highly non-linear combination, depending on what features you're using. And when you use decision trees, you're approximating that with these axis parallel splits and rectangular regions, etc. So I just wanted to make that point. This one, of course, with 10 examples, your decision tree is perfectly describing it. So you don't need anything more than this. This is sufficient for this toy problem, right? But in real life problems, many times there are sophisticated decision surfaces, nonlinear decision surfaces. Decision tree helps us come up with a piecewise linear approximation of that nonlinear surface very quickly. So it's very practically useful, but sometimes it may not be able to compete in accuracy with a method which can directly find that nonlinear surface for you, which can be an SVM or a neural network. That's the division. That's the point I was trying to bring out.
So in other words, maybe I just want to summarize. So in other words, if we have a finite amount of or something that is practically possible, practically possible amount of the decision trees or the if then that we can do, right? Sometimes the if then can stretch even more. So the more it goes, the more difficult to manage as well. We don't know when the particular criteria is checked. So in that annotation, I understand that it's complex as the data set is complex, right? Then it becomes very complex. But if it is a finite data set which is practically manageable, then I think decision trees is a good option to go, right?
Decision trees is a great option to go. Even with some large data sets, decision trees are a great option to go. That's why I said, there could be millions of rows, there could be thousands or even hundreds of thousands of columns. So there are practical problems where large amounts of data decision trees were used. And we will, tomorrow with ensembles, we will see how we can even more expand it. Let's go to Mr. Kannan's question.
Professor, I just had a relative question only, that we have multiple datas and multiple linear surfaces. Would it be possible that we use test data and we do a lazy learning which will give a solve for this, or is it related in the first place and will it give a solve?
Yeah, lazy learning here. Imagine, take away these green lines. So you just have a data set. Can lazy learning or can k-nearest neighbor work there? Absolutely.
Yeah.
So good intuition. Yeah.
Thank you.
Yes. Okay. Now let's go. Let's take a break. Actually, we are 81 minutes into the class, so it's a good time to take a break. 7:51 p.m. in India, where I am. So I'll be back by 8:01 p.m. Indian time.